Hi, my name is Benjamin Wexler, and I will be talking about our paper analyzing and overcoming degradation in warm start reinforcement learning. Warm start reinforcement learning is when an agent is initialized with a pre-trained expert or behavioral policy which we wish to improve upon. Reinforcement learning is effective in dense reward environments but struggles when rewards are sparse. Therefore, warm start reinforcement learning can utilize the expert in order to overcome the exploration issue. In order to obtain the expert policy, we could use imitation learning or through pre-training through RL. And warm start reinforcement learning can overcome this problem of sparse rewards and increase the sample efficiency and reduce training time. However, in our research, we show that when transitioning from initialization to reinforcement learning updates, degradation in the performance of the agent can occur. This degradation is undesirable because it may compromise the agent's safety, especially in real-world robotic applications. We demonstrate in this paper that warm start reinforcement learning degradation is a common phenomenon in continuous environments, in continuous reinforcement learning algorithms. We analyze why degradation occurs. We implement constraint methods to overcome this degradation that comprise of offline RL and online RL solutions. And we show that there's a trade-off between the degradation and final performance. And we propose CCL PQD, where the CCL component constrains the updates using a confidence measure of the value function. And PQD is a novel distance function that we introduce for CCL. And we show that CCL PQD effectively balances between performance and degradation. We demonstrate here our results that show the degradation occurs when not loading the value function and training it from scratch at the beginning for the first 50K steps. We train it offline to pre-train it before updating the policy, but the second we start updating the policy, we see that there's this degradation. But this degradation doesn't occur if we just load the pre-trained QNet from a pre-trained RL algorithm, for instance. We see that this happens in half cheetah, humanoid ant, hopper environment, and many other continuous action environments. We see that the degradation occurs in off-policy algorithms like DDPG, TD3, and SAC, but does not occur in on-policy algorithms like VPG and PPO. And our results show that warm start reinforcement learning converges faster than vanilla off-policy RL, but still takes time to return to behavioral performance. And in our paper, what we really deal with is limiting this degradation. And even though ultimately it learns faster, in terms of safety, this degradation is undesirable. What causes it? The degradation it's reminiscent of the QNet the failure of the QNet to learn when trained offline, which is similar to what happens in offline RL, which trains on a buffer of offline behavioral trajectories and optimizes the policy by maximizing the value function on the dataset. And in that domain too, off-policy algorithms fail to learn offline. And this was identified in papers such as BCQ and Bear, which identify the source as extrapolation error and propose solutions to overcoming the problem. What is extrapolation error? It's caused by the mismatch between behavioral trajectories and trajectories without reward data. That is, out of distribution data. The value function Q of SA, where the action A was never taken, should be undefined. However, the problem is that neural network approximators output values even for trajectories never taken. So some of these out of distribution actions will be assigned higher values for the same state than for the behavioral action. And what this does is update the policy to take those out of distribution actions never taken before, which are likely to be worse than the behavioral action. We demonstrate this using PCA, where we can visualize the Q value function's output on actions that are not the behavioral action, but surrounding it, using added noise added to the action and a random sampling. And we can see that there are these actions that plot to the right of the behavioral action that are assigned higher values, even though they're never taken. And this is at the top is when the QNet is not loaded and is required to be trained from scratch. So we can see this extrapolation error where values are assigned higher to higher values are assigned to different actions never taken. However, we can also see this in the when the behavioral QNet is loaded, and we analyze there that actions also not necessarily taken are also assigned higher values than the behavioral action. So what then is the difference? Why is there no extrapolation error when the QNet is loaded from some pre-trained behavioral policy? The difference is that when training from scratch, the behavioral policy action usually plots in the center of the distribution, and surrounding actions plot around it in a normal distribution. Whereas a properly trained value function plots the optimized behavioral policy towards the higher end of the distribution, making extrapolation error not as much of an issue. We discuss overcoming worm-start reinforcement learning degradation. In order to do this, we constrain the policy updates. And what this does is maintain a proximity to the behavioral distribution, minimizes the effect of extrapolation error, and therefore reduces the probability of entering out of distribution states where the agent has no knowledge and has difficulty returning from. Some of these solutions to constraining the updates are borrowed from offline RL solutions, which usually divide into two categories: policy constraint and policy value function penalty, where we can just try to enforce a constraint on the updates, or using a perturbation net, or we could introduce a penalty on the policy update or the Q value function update. When we do this, we see that there's this trade-off between degradation and performance, where a higher constraint leads to less degradation but lower performance over time, and vice versa. Is there a better approach? Can we relax the constraint over time in a non-arbitrary manner and ultimately shift to vanilla reinforcement learning? Do better solutions for the trade-off between degradation and performance exist? We introduce confidence-constrained learning, where we interpolate between vanilla RL and imitation learning. So in order to determine the value of alpha, we use a percentile to measure the confidence of the QNet, which was shown in our histogram experiments as a good measure. And when the confidence is higher, we assign more weight to the policy gradient objective. And when it's less confident, we focus more on imitation learning. This percentile usually ranges from values of fully random, 0.5 and 1. And we map the percentile to some alpha start and 1 between where alpha star is the minimal safe policy penalty and 1 is vanilla reinforcement learning. When choosing CCL's hyperparameters, we think about alpha start, where in order to determine it, we have to consider the trade-off between safety, limiting degradation, and increasing performance over time. Some environments may be more sensitive if they have a sparse reward or more sensitive actions. And we have to consider the magnitude of the reward and corresponding gradient magnitude. And we also have to consider what kind of distance function we use, KL divergence, behavior cloning. In ours, we use PQD, which is a novel distance function that uses the components of the distance function gradient, which, for example, we use behavior cloning, that do not decrease the average Q value. So when the gradient of the Q function and times the gradient of this distance function is greater than 0, it implies that the scalar projection, the overlap between the gradient vectors, is positive, and that following the distance gradient will not decrease the Q value. When it's less than or equal to 0, then following the distance gradient will decrease the Q value. So instead, we follow the vector rejection of the gradients of D from the negative gradients of Q instead. And what this does is restrict the distance gradient vector to the components that decrease the distance but do not decrease the overall Q value. We look at the results of CCL-PQD, and we show that it eliminates or significantly reduces the degradation. It's competitive with vanilla worm start off-policy reinforcement learning in terms of final performance. It reduces the reduced degradation implies a higher safety guarantee for the robotic agent. It's an effective method for improving upon behavioral policies in dense reward environments, such as half-3D and humanoid, as well as sparse reward robotic environments, for example, pick and place, where vanilla RL fails if we don't use worm start reinforcement learning. Here we can see the results from comparing worm start TD3, where worm start reinforcement learning, with a purple line that has degradation at the beginning of each of these environments, versus TD3, which starts from scratch, and CCL-PQD, which has worm start reinforcement learning, but it doesn't degrade as much and continues to learn. We could see in 10K, it maintains without degradation. Fetch pick in place, TD3 fails to learn at all. Worm start TD3 crashes at the beginning, but CCL-PQD maintains performance and continues to increase, as well as in all these other environments, such as the robotic fetch slide and fetch push and humanoid. We also can look at various other measurements to compare, such as the value at risk and the conditional value at risk, that measure the maximum expected loss and the average loss over time. And we see that CCL-PQD performs optimally in terms of those measurements and metrics. And we also look at this trade-off between degradation and learning, which these constraint methods exhibit. And what this translates to is solving a multi-objective optimization problem where the set of best solutions lie on the Pareto front. CCL-PQD results show that it often spans the Pareto front across the possible values for the constraint factor alpha start. And what this does is ensure that the permitted risk to the agent's safety in favor of performance gains is optimal. Other constraint methods usually plot behind the Pareto front. So we showed that CCL-PQD has a higher advantage. When we plot CCL-PQD in the green, we could see it often placing on the Pareto front for all these environments. And the other methods, such as the perturbation net, policy penalty, also we could lower the learning rate and clip the gradient. And we compare also to on-policy RL algorithms, which usually plot behind the Pareto front. We also have a video demonstrating results that can be seen at this link. And in conclusion, we studied worm start reinforcement learning degradation, found extrapolation error to be the root cause. We explained why out-distribution policies fail to return quickly to behavioral performance. We proposed CCL combined with the novel metric PQD. We showed CCL-PQD significantly reduces degradation and increases safety as a result. Illustrated that there's this trade-off that exists for many constraint methods where higher performance is obtainable where more degradation is risk, and evaluated CCL-PQD as an effective warm start method for sparse and dense reward environments, and demonstrated that CCL-PQD performs along the Pareto front, giving the user this ability to optimally control the trade-off between how much degradation they would like to risk and how much final performance. Thank you.